G'day viewers. In this segment I'll provide an overview of content delivery networks. So CDNs for content delivery network or a content distribution network provide an effective way to distribute content to many clients on the internet. They're both more efficient in terms of how they use the overall network bandwidth, which is good for the network, and they provide faster delivery of content to clients. For these reasons, CDNs have become an important part of the internet architecture today. So as a little bit of context, CDNs emerged in the mid to late 1990s. Really what happened during this period was that the web was taking off and the traffic volumes grew tremendously, more quickly than the network could be expanded. And this caused various problems. It caused problems for a very popular servers. As these servers became very popular, the traffic volumes close to the server grew and grew, and it made it very difficult to provision large servers. The volume of traffic going through all of the networks congested the networks in turn, and there was the need to provision more bandwidth. And finally, for all of this, it gave a rather poor user experience because of congestion and because of pages growing richer and larger all of the time. So in this setting, everyone was really looking for a way to improve the web experience, often by looking at different kinds of caching. But CDNs emerged really as an idea to improve the efficiency of content distribution. The key idea is to place popular content near the clients and somehow hook the clients up to the content that is replicated near them. If we can do this, and CDNs really use a trick today to make this work, a very clever trick. If we can do this, then we'll be able to help with all of those three issues above, as we'll see. So here, actually, this is some slide that I showed you in the very beginning of this course, just about the benefits of content distribution. Here's the architecture as you might imagine it before there's any content distribution networks. In this example, we have here a source on the left, sending to 4 different users on the right here. And you can see that to send, we send through here, 1 copy from the source, another copy from the source, another copy from the source, and another copy from the source. This takes altogether 4 by 3 or 12 network hops, where a network hop is something like this, sending the content from one hop to another hop, between any hops. That's how much work the network has to perform. And you can see that the server has to do a lot here in terms of sending a lot of information out. Well, let's look at what happens when we do use content distribution networks. Here's a CDN architecture. What we've done is inserted this replica here, and now this replica can hold a copy of the content and redistribute the content from that point. And so, of course, what happens is that the source can simply send to this point, and from this point, we can send out to the users who are nearby. So we've taken the amount of network effort needed down to 4 + 2 or 6 network hops overall. So it's twice efficient in terms of the overall network. But it's actually even better than that from the point of view of all of the parties. Let's take a look at that. And here are the kinds of benefits we get, assuming that there is very popular content that many users want. I'll get to this on the next slide. If we have popular content and we have this replica in place and we can arrange for all of the users to use it, then we see the following benefits. We see reduced server load. So that's a benefit right here. You can see the source only needs to send 1 copy out to this replica. And this might not be such a big deal with 4 users, but imagine hundreds of thousands of users all wanting a copy of this content. Then we're going to greatly reduce all of the effort on the source. We're also reducing the network load. So you can see that just if we look at points within the network, like here, for instance, maybe as we get close to ISPs, if these are ISPs at the edge of the network, then the amount of upstream bandwidth they need has fallen greatly also, just in the same way that it has for the server. Maybe it hasn't fallen quite as much, but it's fallen a lot. And finally, we obtain an improved user experience. This should manifest itself as decreased page load time. So the users here on the right should be better off. Why should they get a better user experience? Well, generally, so what they're doing now is they're downloading content from a replica that is closer than the remote server. This is generally faster for several reasons. If you remember from our discussion of web page performance, the round trip time matters because connection setup is involved. If you're setting up a connection to someone who's closer, the ITT will be smaller and you'll be able to do it more quickly. Moreover, we're just going over this local link here. We're not going over remote links. So this means that no bottlenecks further out in the network will be able to slow us down. It's only the local link near the edge of the network that could be a bottleneck. So if we can arrange for this architecture, the CDN architecture, to come into existence, then we'll be much better off. But that's assuming popular content. So let's just revisit that for a moment. Is there very popular content to be distributed? Well, yes, you and I both know the answer is yes, and that there are hugely popular things out there on the internet. What I'm going to do is just tell you a little bit about the distribution of popular content on the internet to put that into perspective. It turns out that, well, some of you might have heard of Zipf's law, named after George Zipf, who's shown here on the right-hand side. Zipf was a linguist, and Zipf's law relates to the relative frequency of words in a language. The most popular word, I guess that would be the or something in English, we'll give that relative frequency 1. The second most popular word is half as popular as the most common word. The third word is a third as popular. The fourth word, a quarter as popular. The fifth word, a fifth as popular, and so on. So the popularity of the kth item, shown here, is 1 on k compared to the popularity of the most popular item. This law, or relative ranking of frequencies, turns out to be something that is very common in the real world. So it is not simply the relative distribution of the frequency of words in a language. It also describes well, the popularity of video rentals. When we used to have video stores, online now I guess, the distribution of incomes, how they fall off. What else? The size of cities, many different things, the size of the population of cities, many different things roughly follow Zipf's law in terms of their distribution. Now, and what this means for us in networks, and the content does, I mentioned video as an example, but other popular websites too. What this means is that there is a small number of very popular items. These items, if we can put them in the replicas, will save an enormous amount of work because essentially everyone was looking at them, or a large fraction of the internet was looking at them. But Zipf's law also tells us, you might be somewhat surprised to learn, that there is also a very long tail out here, and that tail matters because while all of this other content is unpopular compared to the popular stuff, there is a lot of it. This is sometimes called the long tail. You might have heard that expression. And the idea is that the weight of the long tail is significant. When you add it up, it's going to matter. It can even dominate the popular items. So even if we're able to sort of use caching techniques on all of the popular items, we're still going to need a lot of network bandwidth for the unpopular ones. That's what I'm saying. We would really like to optimize for both of these cases. For CDNs, however, the good news is this. There are many popular items, so we can use replicas very well. Well, this begs the question of how we're actually going to do it. I'm sure you've got the architecture down now. The question is just, how do we cause content to be distributed in that way? We saw something that gets a little close. I mean, if we just have browsers and servers, we don't have a content distribution architecture yet. If we put in the caches at browsers and at proxies, well, we're a little bit of a step closer in some way. A cache is a replica of the content. Now, if we just have a browser cache, well, we've got a replica there, and we're saving when the same user goes back to visit the page. But we haven't helped all of the other users who are nearby. Well, if we have a proxy cache, actually now we're caching across all of the users in that organization. So we're doing a little better. But we maybe haven't helped a lot of other clients who are nearby. A proxy cache only helps someone in your own organization. So neither of these methods really help all of the nearby clients to use the closest replica, nor do these methods really help with the deployment. There's something that sets of users have to do for themselves. So if you are a business and you want to be able to deploy these replicas to improve your site, well, you're a little stuck. You would need to wait for the world to deploy all of their proxies. Instead, we would like a way to be able to place these replicas ourselves. So for a site that wants to improve its experience, it could place replicas essentially all around the internet, distribute some of these worldwide. And we would like these replicas to be for use by all nearby clients. So a client should use the nearest replica. That's where we're going to get the advantage. How do we do this? I still haven't told you yet. Well, the answer, I'll tell you now, is that it's done by the clever use of the DNS. So the DNS mapping between host names and the IP addresses of the replicas is what's going to make it work. Let's see a little more. Here's the architecture overall for the content delivery network. I showed you before, so we have the origin server up here on the top. And before, we'd really sort of been looking at going to one replica and the clients associated with it. But just here for clarity, I've shown you that there are other replicas here and here in widely geographically distributed locations. And we would like the client to contact the nearest replica. So this client here is going to fetch a page from this replica here because this client is closest to Sydney. Whereas another client over here is closest to Amsterdam. So that's where it will fetch a copy of the page from, that replica. That's what we want to arrange to happen. Now we just have to do it with that clever trick of the DNS. Well, here's how it works. To contact a site and get the image off the site, you need to use the DNS to resolve the name of a server that has the content you want into its IP address. For content delivery networks, we upgrade the DNS server so that DNS resolution of a site, of the host name for the site, gives different answers to different clients. The answer, of course, that we want is to tell each client the site that is nearest the replica. Right? So that's what we want to do. So you can see here, if there are clients in Sydney and they want to access a certain site that has been replicated around the internet, they will they'll issue a query to the DNS somehow, and here is the DNS server for the CDN. This bit has been upgraded. The clients haven't been upgraded. The DNS will answer, and what the DNS server knows here is it knows who's asking for the translation. So in particular, you could look at the IP address on the DNS query. That would tell you actually probably not the client, but the client's local name server, which should be close to the client. Look at the IP address of the name server. You can use internet mapping techniques to try and work out what's closest. And for the Sydney client, when it's asking, the right answer that you want to tell it is to contact the Sydney node here, because that's closest to it. On the other hand, when you get a request from someone over in Amsterdam, you're going to be able to work out from the IP address that's on that DNS request that this node is actually a long way away from the Sydney replica. The answer you want to send back is the IP address of this replica in Amsterdam. Now, what you could imagine doing if you wanted to work out how some of this mapping works is when you've got a query from a node, you could ask all of your replicas to ping it or trace route to it if you wanted, and just see how many milliseconds each replica was from it. And over time, you could build up a map of where the different IP addresses were and work out how to provide the right answer more quickly. So the whole trick here is that the DNS server for the CDN is a special one that provides a different answer for all of the different clients to connect them to the nearest replica. You might think this is a little bit of a cheat in that when we talked about the DNS before, we had a file where you had the IP address of a DNS name, and it was the same for whoever was asking. But there was no requirement that it be the same for whoever was asking. And we actually don't break things really by returning a different answer in response to different clients. So this, if we simply do this, then we've accomplished our content distribution network. Now our clients in different places will contact the replicas. We still need to, from the origin server, distribute the content to these different replicas, but we can do that with the system we put together fairly easily. And it's also the case that the site that's served by this CDN, well, we'll have to have a special DNS server for that, for the host name for that site to do this processing. But that's exactly what CDNs do. And finally, to close with CDNs, I'd just like to remark on their business model. Essentially, CDNs come up with a very clever business model. This was pioneered by Akamai, which was founded at about 96 and was well underway by the late 90s. And the observation for a business model here is that placing a replica of a particular site at an ISP is a win-win situation. You help both parties. So you can both improve the site experience, well, that should be worth money to the consumer site, and you can reduce the bandwidth that's needed by the ISP where you're placing the replica. Well, that should be worth some money to the ISP in some form. For this reason, because deploying these replicas are really win-win, CDNs have become an integral part of the internet architecture. And I would add, in terms of deployment, maybe one of the reasons their deployment took off is it's possible to deploy this replica simply by upgrading the DNS servers for the particular domain managed that's run by all of the replicas without changing any other ISP software and without changing any of the user clients that were running browsers to use the web. So without changing them, we've managed to redirect them to these nearby replicas, which is pretty cool. Okay, so now you know how CDNs work.